Okay, so routing information protocol is based on the distance vector algorithm. It's, runs on top of UDP at port 520. I didn't cover the transport layer protocol, but you are familiar with the concept of ports. UDP is a very simple protocol. So port 520 on UDP is used by RIP, and it used to be called the software which implements RIP is used to be called Route D in BSD Unix. Okay, these are the solutions that are coming up. So I wanted people to come up with solutions to the count to infinity problem.
Ma'am?
Yes.
Ma'am, can't a router directly give the weight of a not reach, like when a router loses a network, can't it just give its weight as infinity directly there?
Yeah, it can.
So won't that solve the problem?
So explain how that will solve the problem. So you're saying R1 loses the connection. Instead of removing the entry, it is going to mark it as cost 16.
Yeah. Then
Yes?
yes, ma'am.
Yeah. So when R2 advertises the network,
Okay.
what
Lesser
will happen?
than lesser
The
versus
cost is less than the cost you already have, so it still holds it. I mean, it basically updates the entry still. Though I'm not saying that's a bad solution, having it as 16, but after having it as 16, what else should you do to prevent this problem? See, what is the timing of the messages which is creating the problem? When will it not create a problem, even though you have, let's say you have 16 marked, okay? The cost is 16 marked, okay?
yeah.
You don't remove the entry. Instead, you mark the entry as 16. Then what sequence of messages will not create the problem? What sequence of messages will create the problem?
If
It's a
it
very
receives an
timing
update,
dependent problem. Yeah.
yeah, if it receives a message after, so if we stop it from receiving a message during updation, it won't be a problem, right?
No. I mean, see, please remember that every router is periodically broadcasting its routing table to all its neighbors, right? So it's a very, very timing oriented problem. Please note that there is messages going from R1 to R2 and messages coming from R2 to R1. When will the problem be triggered if you maintain the cost as 16 instead of removing the entry? And when will
If
it not be triggered?
it will be triggered if it receives a lesser value.
Yeah, so when will it not receive the lesser value? When is it unlikely to get them? When is it impossible for it to get a lesser value from R2?
When it broadcasts first to
Which
R2.
broadcast first?
R1 broadcasts with the entry as 16 to R2. Then R2 will have
Right.
to update it because of rule 3.
Yes.
And so
So,
after that, it will not change it.
yes. So the sequence therefore has to be R1 loses connection to N0, marks the entry as cost 16, advertises that to R2. R2 updates its entry to 16 using rule 3 because the same neighbor has advertised the same network with a different cost. Now when R2 advertises its routing table, the cost will be 16, therefore anyway, it will not be updated in R1. So this, therefore adding, updating the cost to 16 instead of removing the entry does help. It only fails when the sequence fails, right? So
Yes.
in the earlier situation where you removed the entry, it didn't matter. Like, you always ended up adding an entry for N naught through R2, which was wrong, right? So updating the entry to cos 16 is useful because only if you get the advertisement from R2 before you advertise it to R2, you will have a problem. How do you solve that problem? How do you prevent, how can you prevent R2's advertisement coming to you before you send your information to R2? Is there some way you can sort of speed up the advertisement to R2?
Can we use timestamps like when R1 removes N naught, it maintains a timestamp at which it removed, and then when the broadcast it sends from R2, it sees that the timestamp for N1 is older, hence it chooses not to update it.
Yeah, but in networks, you will notice that there will never be timestamps used for anything. The reason being that different systems can have different times, right? They may not be synchronized. And that can lead to serious havoc in the networks if you make an assumption that the clocks are synchronized of the systems. So they don't believe in synchronization using clocks on systems. In fact, I haven't talked about the encoding, the Manchester encoding in Ethernet, which is what is called as a self-clocking mechanism. How do you synchronize two systems is the question that is solved in Manchester encoding, where you don't explicitly synchronize the clocks of the two systems. Similarly, when we see further in TCP, I don't know if you people did the Nagel algorithm in TCP or not, or you remember or not, but it's a self-clocking mechanism again. So please note that it's all about timing. So, you are periodically broadcasting the routing table. Can you do something better than periodically broadcast? You can't avoid broadcasting periodically because you basically learn that a particular router is alive and is fine by the periodical broadcasts. If you don't get periodical broadcasts from the router, you wait for multiple periods like that, because please remember RIP is especially using UDP. UDP is an unreliable protocol. So I'll send a broadcast. It can get, corrupted and lost. So I lose one message at the end of one interval and I say, oh, this router is down. That was bad news. So what you usually do, you wait for multiple such cycles and then remove the entry if you didn't get a single broadcast in that period. Okay, then you assume that the router is down. Here, what the particular example we have taken, an interface of the router is down. So an edge is down in the graph, not the node. When the node goes down, then you have to detect it, and you have to detect that all routes, all networks reachable through that node or router are to be removed, right? So how do you detect a node has gone down in the network? Because you're not getting periodic broadcasts from the router. Therefore, you need broadcasts, periodic broadcasts. There is no doubt about that. But is there something you can do when something changes in your routing table? Okay, that's one question. Second question is, I tell some information to Bharadwaj, right? Like, for example, today I called him up and said, let's come on 10 minutes late because things are running late at home. I have to do still some things before I can come on to the class. Okay. Should Bharadwaj inform that to me also?
No.
So can you apply that logic to the network? Okay, so the first solution is this. do not advertise back on the interface from which routes are learned, or do not advertise back to the person who informed you or something, right? Somebody tells you something, you don't tell them back the same thing. Okay, that is what is the thing here. So if you look at this is still not saying that I'm adding a cos 16 here. I'm removing the entry for n naught from R1. However, the advertisement from R2 will only contain N2 in its advertisement because N2 is the only network it knows from an interface other than ETH0. Okay, it's advertising this information on ETH0, therefore it advertises only N21 on ETH0. Now R2 will also advertise on ETH1. When it advertises on ETH1, it will advertise both N0 and N1 on ETH1 interface. Okay, I haven't shown those advertisements in these pictures, so please don't assume that R1 advertises only to R2 and R2 advertises only to R1. No, we said that every router broadcasts periodically on all its interfaces, right? So that is what you have to be careful about. So in this case, we are not advertising N0 and N1 on this interface because we learned about N0 and N1 on these interfaces. Now this solves the problem. Actually, in this particular topology, this is sufficient, necessary and sufficient condition to avoid the count infinity problem. But this is not true when there are loops in the graph. Okay, I'm giving you some answers which I don't want normally to give. I want you to work out how using this solution, which is called as the split horizon solution to the count infinity problem, is sufficient for avoiding the count infinity problem when you do not have a cycle in the graph. But when you have a cyclic graph, it's not sufficient. I would like you to work out that by yourselves. Okay. Second solution, this is what Farzeen has suggested. Use the cos 16, don't remove the entry. Okay. How is this an advantage? Because if you didn't do this, right? What are you doing in your advertisement? You are including N0 16 to R2. So R2 has to update it because the same neighbor is advertising same network with a different cost, right? Earlier, when you removed the entry, what would R1 do? It would only advertise N1 and N2. Okay. Now N0 would not be updated nor refreshed. Okay. The refreshing means what? You basically reset the timer. Okay. Every entry when you add, you start a timer. At the end of that timer, if you have not updated that entry is removed from your routing table. Okay. Now, if you don't send N0 from R1, then this entry is not updated with every broadcast cycle. So depending on the timeout period, supposing you say for 3 broadcast cycles, if this entry is not updated, then I'll remove this entry. So, and RIP uses a broadcast interval of 30 seconds. So every 30 seconds, it advertises its routing table. Okay, every router advertises every entry in its routing table every 30 seconds. And the timeout for this is, let us say, 90 seconds, right? So until 90 seconds, this entry of N0 remains in R2. So at some point, R2 will advertise it to R1. R1 doesn't have an entry for N0, so you'll get into the count infinity problem. Okay. But if you can make the cos 16 and include in your regular broadcast, then it is updated to 16, and it helps to reduce the probability that you will end up in counter-immunity problem. So spread the bad news fast. It's called a poison reverse solution. Okay. Third solution is what is called as triggered updates. Something changes in your routing table, do not wait for the next broadcast cycle. Advertise it immediately so that the changes get propagated very fast into all the routers. So when I notice that my interface has gone down, so here I'm applying both my solutions of increasing the cost to 16 and also advertising it immediately to R2. So I'm not waiting for my next broadcast cycle unless the previous slide, okay, in the previous slide, I waited for my next broadcast cycle and advertises the entire, no, I have advertised the entire routing table there, but here I'm only advertising the single entry which has been modified. So advertise only the modified entries and immediately. So the probability that somebody else will tell you about your own thing will be reduced. Okay. The last thing is called hold down timeout. Okay. Hold down timeout says if you have updated an entry to infinity, which is 16, do not update that entry immediately if somebody says I have a better route. Why? This is basically, I have informed Bharadwaj something, right? And he has to inform to all of you. In today's world, you people have a WhatsApp group, so he'll put it on that, and it's assumed everyone instantaneously comes to know what is the news. But some people may not see WhatsApp every day, every minute, whatever, right? So if I tell you now, if I tell him at this minute something, and I assume that in the next minute everyone is aware of it, it's not a very good algorithm because I'm not giving time for that information to be propagated to everyone. Okay. So that is the basic idea behind hold down timeout. What is the idea? You are assuming that if I inform my neighbor that a route is unreachable, that neighbor has to inform its neighbors and so on. So if there is an alternate route, it's okay. Another possibility is somebody can reach this network only through me, but they have not yet received the information that I have lost my connection. So I will not update my entry when I have marked it as unreachable immediately. I'll give time so that this information spreads to the whole network. And even after that, I keep getting some better routes. It means that there are alternate paths to that network and I can use it. I'll update it at that point of time, not immediately. So this is the hold down timeout. So these are the 4 solutions that RIP uses. Okay. Now RIP version 1 and version 2, there are 2 versions. RIP version 1 uses broadcast, whereas RIP version 2 uses the all routers multicast address, which is 224.0.0.2. How do you see route, the groups your system has joined use the netstat minus G command. Okay, netstat minus GN will show you what groups your system has joined. Okay. RIP version 1 supports only classful addressing. RIP version 2 supports CIDR, which means what? It advertises not just the network ID, but it also advertises the mask information, because you don't know now, given the network ID, what is the mask, right? 10 doesn't mean mask is 255.0.0.0. It means something else. So the RIP version 2 message contains the network ID, the mask, as well as the next hop. Okay, it carries also the gateway information. It helps to reduce the countability problem because, if somebody says, I learned about this network from you, you don't have to update that information. So it, is much easier to avoid the countability problem in RIP version 2. Okay. So this is the discussion on distance vector algorithm and routing information protocol.